All right. So the first announcement is I didn't do any work this weekend. I took the weekend off. Like I said, for me, it's a new thing. I'm trying it this semester. It's kind of nice. But I have a ton of emails and a ton of grading to do. So if you turn something in and you haven't heard back from me, that's why. Once I'm caught up, I'll feel like I haven't graded something or I missed something. Or if you have questions about a grade that you got, Any questions about that? All right, to remind you for independent work, by now you should have about 14.4 points. I did glance at my email and I did see that some people turned some independent work in. I should also remind you the way you're supposed to do it, if it's a written assignment, is go to Google Docs. So almost the same way you do lab, right? So you're doing it in Google Docs and it's shared with me. It's kind of the same way. So go to Google Docs, write your papers there, make sure it's shared with me. It's not like you're going to get in trouble or lose points if you don't. Like, for example, the one I just saw online, they sent me a PDF, and that's fine. They just said, all right, I just need you to copy that and paste it into Google Docs. So any questions about independent work? Okay. Let's see. Michaela? Okay. And see if I can get this. Is it Brody? Yep. Good morning. Massey. Is there anybody I haven't called? Everybody's accounted for. Morning. Pretty good. It's Eric, right?
What is it?
Eric?
Cody, the transfer.
Oh, all right. I'll talk to you after class too then.
Okay.
We've got two new students. Fun. All right. Anybody else I haven't called? I think we're accounted for so far. Less than a minute. What else? What were the other reminders? Independent work. Obviously, if you're online right now, if you're live streaming, the 6 of you, we're gonna do it like we've been doing it. I'm gonna give you words. At the end of it, send me those emails sometime before 9 a.m. If it's after 9 a.m., it's too late. So send me those emails or those words. You don't have to do screenshots unless you're watching the video. So those 6 of you who are online right now don't need to do screenshots. If you're watching the video that I posted to Google Classroom via YouTube, then you'll need to take the screenshots when I do the attendance words. Good morning. So any questions about attendance? All right. Cedric's here. Everybody's accounted for. Not quite 8 yet. I'm going to wait till it's 8:01 before we get started. What else? Oh, yeah. So like I said, I haven't done any grading, which is good and bad for you in a way, right? So how do I put it? So when I go around to grading the lab, for example, as long as it's done before I go get around to grading it, then I consider that on time. So, if you turn it in on Saturday, even though it was due on Friday, it doesn't matter to me, at least not yet. Same with the pre-labs. So if you haven't done your pre-labs yet, go ahead and knock them out because as long as it's there before I get to it, I'm going to consider that on time. It's 8 o'clock. So any questions about lab or independent work or attendance?
I do it.
Yes.
So I know there's not really like a format.
Uh-huh.
Double space 12 font.
Yep.
And it's not really a requirement, but I guess the topic. Can you give us examples of
Yes and no.
biology itself?
That's a great question. So for those of you online, if you didn't hear, it was about independent work, basically give you some ideas of some topics. I'll think of some and try to write them down and share them. But also, like I'm sure some of you have noticed, I try to give ideas throughout the lecture. Because like as we talk about something, I'm like, oh yeah, that's a good idea for independent work. So yeah, definitely take note of that. And again, the reason I don't really give too many options or ideas anyways, because I kind of do want it to be yours. Like I'm more than happy to help. But like something I might find fun, you might find boring. He might find it extremely exciting, right? So the idea is for you to find stuff that you're interested in. Because I'll be honest, I love biology, but I can see how this chemistry stuff would be boring. And then next we're going to learn about like osmosis and all the different types of energy. And I can see how that would be boring. Like biology to me is the fun stuff. It's like the wilderness for me, right? That's the kind of stuff I like, animals and plants and the environment. Well, someone else might like laboratory stuff, right? Things that are done in test tubes. So great question.
We get to pick the topic. It's just
Yep.
biology.
Exactly. As long as it's about biology, you pick the topic, you can write about it. Great question. Any other questions? All right. It is 8:01. so we will officially get started. I guess the first word for attendance, since it's just right in front of me, is remote control. And again, as usual, if you're in person, you don't have to send any words, but you will get a little extra credit if you do that. So yeah, the first word for attendance is remote control. And I guess if you're watching the video, you take a screenshot of me holding the remote control. All right, let's jump back into it then. Let's finish up chapter 2, the chemistry chapter. We left off with this big bullet point here. We were talking about, hold on, let me get this fixed here. We're talking about water. That's the last thing we're going to talk about. So to remind you, what you need to know to understand what we're about to talk about is the fact that water is a polar molecule. So if you remember, the electrons aren't shared equally, right? The electrons like to hang out near the oxygen more than they like to hang out next to the hydrogens. Therefore, the oxygen end of the molecule is slightly negative, the hydrogen end is slightly positive, and therefore they attract each other, right? So that's what we're talking about when I say hydrogen bonds and polar molecules. And if you remember correctly, that's what we talked about when I said all these things that we're going to talk about water, mostly boils down to that. And we left off talking about the cohesion of water. You guys, somebody knew what cohesion was, right? It's when things stick together, things of the same type. In this case, we're talking about water molecules sticking together. So what happens is, like, and your book just gives us an example of why that's so important, the fact that water is cohesive. Imagine, like, how does water get to the top of trees? Especially when you think about like sequoia trees, 300 something feet tall. How does the water get from the roots to the very tippy top, leaf? It's not like there's water pumps. And the answer is the cohesion of water, right? So that's one of the reasons that's so important. And you can look at this picture, at the bottom right, this drawing right here. So as one water molecule evaporates out of the top of the tree, for example, it pulls the rest with it. They're all hydrogen bonded, right? So that's how the water moves its way up. As far as the exam is concerned, I'm probably not going to ask any examples about this. Just know that the cohesion of water is one of the life-giving properties of water. Your book also gives this example when we're talking about cohesion of water, which is surface tension. Basically, surface tension allows, certain animals, certain things to basically stay on top of the water. And again, that's just an example. I'm probably not going to ask you anything about it. If anything, for the exam, you just need to know when we're talking about the properties of water that give it life or make it life-giving, the fact that we have cohesion of water. So any questions about that? All right, I've got another picture of surface tension. This person's actually, as you can tell, it's a swimmer, right? What you can't tell is the water level's right here, about right there. So this person has broken the plane of the water, but they're still underwater because of surface tension. It's just an example. Obviously, I'm not going to ask you any questions about Olympic swimmers. There's another picture I found on the internet of surface tension. All right. So any questions about the cohesion of water? All right. This next one's a little bit more important. Has anybody here ever been to a desert? No? Well, never mind. So you might not get this, or at least you won't have first-hand experience. But very often in the desert, it's obviously, as you might imagine, really hot during the day, right? But then in the evening, at the nighttime, sometimes it's actually a little bit chilly. Can anybody guess why that might be? No guesses? That's all right. We'll talk about it. Because water has a very strong resistance to temperature change. You need to know that. Know that. Something that we're going to talk about next chapter that I think you should have been presented with this chapter is what temperature is. What exactly is temperature? The book doesn't really get into it. But if I say the air in this room is getting warmer, does anybody know what that means on the molecular level? What's really happening to the air in the room as the temperature increases? Yeah, molecules are shaking faster, right? They're moving more. So basically, at the molecular level, that's what we're talking about when I say there's an increase in temperature. What I mean is there's an increase in movement. Likewise, when I say there's a decrease in temperature, there's a decrease in movement. Now, the reason that's important is because, again, water is a polar molecule. They're hydrogen bonded to each other. Have you guys ever seen or been in a mosh pit? You guys even know what I mean by mosh pit? You have a bunch of people just flailing around, heavy metal music playing. You guys know what I'm talking about? Can you picture it? So they're all bouncing around, right? Bouncing off of each other, sometimes pushing each other, hitting each other. But they're moving around a lot, right? So if those were molecules, that would mean it's really hot. But then imagine if they were all holding hands, right? let's say, or imagine we did that and had everybody just all hold hands with each other, probably getting a lot of trouble or a little trouble. And then I said, all right, guys, I need you to just bounce around like you're in a mosh pit, right? But you're holding hands, so you're doing your best, but you're not bouncing around that much, right? Because you're all attached to each other. So you're moving as much as you can, but it's not a free for all, right? But then eventually, if you get strong enough and move around enough, eventually you're going to hit it, do it so hard that you're going to let go of each other's hands. Does that make sense? And then you can really start moving around. You can do some spins, some forward rolls, whatever you want, right? Because you're no longer attached to other people. That's basically what happens with water. That's why it can moderate temperature so much. Because as you apply heat to the water, yeah, it's heating up. It's absorbing that heat. It's absorbing that energy. And yes, the molecules are moving around a little bit, but they're stuck with each other, right? They have those hydrogen bonds. So yeah, they're moving a little bit. But it isn't until you put so much heat in there that they break those hydrogen bonds that they really start moving around, and that's when it gets hotter, right? Or reverse if we're talking about things getting cold. And again, that is why water is so good at absorbing energy and not changing the actual temperature much, which is important. This is why we have relatively mild winters. I'll show you, I'll give you an example when I show you the map later, but that's why things are relatively mild around here, because we have not just water, in the ocean or in the rivers or whatever, but water in the atmosphere, humidity. So any questions about that or this slide? Has anybody ever seen, like on stoves, people sometimes keep like a tea kettle full of water and they put it over the eye when they're done with it? And that's why, right? Because that water absorbs the heat from the eye without getting too hot itself, which is really good, especially in the summertime when you're trying to cool your house. You don't want to make it really hot. All right, so if there's no questions about this, let's move forward. Yeah, obviously, sorry, I didn't mention this, but it should have go without saying. The reason that's important for the context of this conversation is because we have life-sustaining temperatures, right? It's not too hot on Earth. It's not too cold on Earth. I mean, there are some extreme spots, but generally speaking, the reason we can have life on Earth is because the temperatures are okay, right? The temperatures allow for it. And one of the big reasons we have that temperature sweet spot, so to speak, is because of the water. And of course, and there's evaporative cooling. So that's the next thing. You would know it as, I'll show you later, but evaporative cooling is basically, you would know it as sweating, right? So here's an example. Here's what I was talking about. Here's London, right? Way up here. If you were to draw a line, that's pretty far north, right? That's about where southern Alaska is, right? And here's where we are, about right there, right? Much lower. We're about where, I don't know, the Mediterranean is, if you were to draw a line. But I don't know how many of you are familiar with London weather, but it's not too much different than ours. Like right now, they're probably having it. I mean, there's different weather patterns, but it's about the same, right? They have about mildish winters, mildish summers. Sometimes it gets really hot, sometimes it gets really cold, but for the most part, it's a lot like it is here. But again, look at this huge difference. Why is it then that they have our weather when they're way up there? I mean, look, that's where Canada is. So how is that possible? How is it that they have about the same weather that we do? Any guesses? And I don't expect you to know. I'm just curious if you know. That's all right. So water basically in the Atlantic Ocean goes like this, right? The water in the Atlantic Ocean or Northern Hemisphere basically does a big circle. So here on the equator, it's getting nice and hot. It's getting heated up by the sun, and it goes up. And because it's really good at retaining temperature and not changing its temperature, as it moves forward and goes north into these cold spots, it's still relatively warm. It still has all that heat that it gained in the equator. And then when it curls over there and hits the UK, it's still relatively warm. All that water is relatively warm. And that's why they have relatively mild winter. Meanwhile, they're that far north. Make sense? So again, I'm not going to ask you questions about this on the exam. This is not a physical geography class. The point is, water does a really good job of not changing temperatures, right? It can absorb a lot of heat and slowly put it out. And again, that's why deserts can get so hot in the summer or in the daytime, because there's no water there to absorb all that heat. So things just get really hot. And then the sun goes down. If there was water there, then the water would slowly put that heat back out. But there is no water there, so it just gets really cold very often. Not always, depends on the desert, but that's how it works. So anyway, any questions about this? All right, and then again, there's a picture from your textbook. Evaporative cooling, aka sweat. That's an independent work topic if you're interested in it. So we all know when humans get hot, we sweat, right? That's how we cool off. But not all animals do that, right? So other animals have different ways of doing it, like panting, right? So they cool off with their tongue, or like elephants cooling off with their ears. So that's something you could look into if you want for independent work. What are some of the other ways that animals regulate their temperature? All right, so any questions about how water moderates temperatures? All right, the next word for attendance, since it's on the slide here, is ice. If you're in the video or you're watching the video, not if you're live online right now, but if you're watching the video that I'm going to post later today, you would take a screenshot of the word ice. So let's talk about the biological significance of ice floating. First of all, let's talk about why ice floats. And you probably already knew this, but why does anything float? Any guesses? Of course, it's kind of right there in front of you, but don't look at the screen. Does anybody know why, generally speaking, things float in liquids? No guesses? It's right there. It's because they're less dense, right? Things are less dense, so they float. Sometimes even other liquids, when you put them in when you combine two liquids, whichever one's less dense will rise to the top, right? Things float that are less dense. And ice is interesting that way because when most things get cold, they get smaller, right? Because like I said earlier, when things get smaller or colder, there's less molecular movement, right? So because of that, things get smaller. Ice is a little bit different. It kind of gets smaller, but then it gets this a certain shape. And because it hits that certain shape and freezes there, it's actually less dense and it expands. And because of that, it floats. And that is actually, well, here's a picture of what I'm talking about, right? So here's these water molecules. It kind of looks blurry. That's not a problem with the projector. That's actually how the textbook tries to make it look. Can you see those blurs? They're trying to show that those water molecules are moving around like I described earlier, right? Because they're liquid. But eventually they get so cold that they stop moving around. Like I said, they form this shape. You don't have to memorize that shape. That is the actual shape. And because they're stuck in that shape and they're farther apart, they're less dense, and they float. But here's the more important part. Why does that matter? Is there any guesses of why it matters that ice floats? How does that matter for life?
Not really a big word, but it helps us find it.
I like that. That's what I was thinking too, because when I was looking at this picture, when I asked that question, I looked at that picture and I thought, that's kind of misleading. The picture's misleading because it goes along with what you're saying. So you're not incorrect, but there's a bigger reason why it's important. But it has nothing to do with that picture. Let's talk about it. It's basically this. There you go. As a body of water cools, the ice layer forms on top. I'm sure you know that, right? You see it on top. Plus, we just talked about the fact that ice floats. And that's important because it's basically a blanket, which may sound weird to you because when you think about a blanket, you probably think of warmth, right? But ice is warm in a sense. It's all relative. So as things freeze, right, that water freezes and you have this blanket of ice, the temperature on the outside, the air temperature can drop even more than the ice, right? So the air is even colder than the ice. The ice is relatively warmer than the air. And because of that, all the water that's under it is protected from that really, really cold air. If that didn't happen, if the ice sunk, then there would be no water, right? So the oceans would freeze over. The lakes would freeze over. And yes, there are some organisms that can survive that. But life as we know it, there's a lot of organisms that can't survive that. They're not evolved for that. So if it wasn't for ice floating, life as we know it wouldn't be the way it is on Earth, including us probably. Because remember when we first started talking about this on Friday, I mentioned that life started in water and eventually moved its way on land. And I hypothesized that maybe that would not have happened. Or certainly wouldn't have happened the way it did without this fact. And if evolution didn't happen exactly the way it did, we wouldn't be here. At least that's the prevailing theory. Anyway, any questions about that? It's pretty simple stuff. Ice floats. You already knew that. To study for the exam, you need to go drink some water with ice in it, right? Ice floats. All right. Now let's talk about the next one. Water is the solvent of life. Before I even get into that, all right, imagine if I had a bunch of Legos. They're all the same shape. They're just different colors, right? I've got a bunch of blocks that are red and green. Now let's just go black and gold, right? Let's do school colors. Big old block this big. They're all put together, and they're, like I said, black and gold. And I give it to her. I say, I need you to make me black box, right? And I'm giving you just a big old box of black, put together, black and orange, or excuse me, black and yellow. What would be the first thing you do when I give that to you? If I say, I want you to make me, I don't know, let's just change it up. I want you to make me a black car. What would you do? What would be the first thing you do when I give you that big old block of yellow and black Legos stuck together? Yeah, you might do that. But literally, try to put yourself in that, right? That's hard. I wish I had it. It'd be easier to visualize. Maybe I'm not explaining it properly. Just imagine a bunch of them stuck together, the yellow and the black, all stuck together in one big chunk. I'm like, all right, here's this, but I want you to make me a black car out of that. Yeah, you have to separate them, right? Because I'm asking you to make me something black, but I didn't just give you black Legos. I gave you a bunch of them, right? That's where this comes in. So keep that in the back of your mind. Let's talk about the water as the solvent of life. First thing you need to know is these three words. I'm going to use them, especially in the first portion of the semester. You need to know what they are, what they mean, how they relate to each other. The first one is a solution. A solution is a liquid with a homogeneous mixture. And if you're taking notes, as far as I'm concerned, you can even get rid of homogeneous because I'm not going to get tricky with it on the exam. As far as I'm concerned, a solution is just a liquid that has stuff mixed in it. Iced tea is a solution. Margarita is a solution. Coca-Cola is a solution, right? It's just a liquid that has stuff dissolved in it, basically. So the dissolving agent, the thing that does the dissolving, that's called a solvent. The thing that's getting dissolved is called the solute. Going back to the margarita idea, any of you have ever made margarita from scratch? You're supposed to make something called simple syrup, which is where you take water and you boil it, and then you mix in sugar in it, right? And then that gives you simple syrup. In that situation, the water would be the solvent because that's the dissolving agent. The sugar would be the solute because that's the thing that's getting dissolved. And then the simple syrup would be the solution because that is the liquid that has the stuff mixed in. Pretty simple, right? I think it's a really simple concept. It's just sometimes hard or easy to mess it up in an exam situation because they all start with S's, right? Solute, solution, solvent, right? It gets a little bit confusing just because they sound similar, but I don't know. If anybody comes up with a good little trick to help you remember which is which, let me know. That's just one of those things I just had to memorize as a student. Anyway, any questions about the relationship between solution, solvent, or solute? All right. And then your book goes on to point out that, when you dissolve something in water, technically that's called an aqueous solution. So not just any old solution, an aqueous solution. All right. Your book also points out that water can dissolve a variety of solutes, and it provides a medium for chemical reactions. So water, again, because it's polar, because they have those hydrogen bonds, it's really good at dissolving stuff. Because if it's trying to dissolve, for example, an ion, which you learned about earlier that you need to know eventually. Remember, an ionic compound is like, a positive thing and a negative thing mixed together. They're stuck together because they're opposite charges. Well, remember, water is slightly positive. It's also slightly negative. So we can get in there and disrupt those ionic bonds and dissolve stuff. It's really good at dissolving stuff because of the fact that it's polar. And that's basically what I'm going to show you on the next slide. And again, your book is using salt as an example. So I'll just show you a picture of it. There we go. So this goes back to the Lego thing. So you might think, your body does need sodium. Your body does need chloride. But when you eat sodium chloride, you're not giving it sodium or chloride. You're giving it sodium chloride, right? It's stuck together. It's like the same way I was trying to picture. I'm giving her a bunch of black and gold Legos. Well, she needs to separate them. If she needs gold Legos, she needs to separate them from the black ones. Same here. Your body does certain things with salt. It does other things with chloride. It doesn't necessarily need sodium chloride. It needs to dissolve it. It needs to get that sodium by itself and the chloride by itself. So again, as boring as that may be, it's even boring to me. It is very important, right? We couldn't have life on Earth, at least not the way we know it, without this happening. So are there any questions? Obviously, that's just an example. I'm not going to ask you again. I mentioned this before. You don't need to memorize the fact that the chloride is negative and the sodium is positive. That's not important. Not at this level. And the last bullet point of the chapter, This is probably more important as far as the lab is concerned because we're going to be doing this in lab this week. It's a two-part lab, as I'm sure you know, because you've already done the pre-labs. But the first part is about drawing molecules, and the second part is all about acids, bases, and pH. So here we go. Let's talk about it. This is historically, probably this is the hardest part of the chapter, I find, for as far as grades are concerned. This seems to be the part that confuses people the most. So what is an acid? You need to know this for an exam, It's basically a compound that releases hydrogen ions. So in a sense, if you were to shorthand this, like for flashcards or whatever, it would be really good to write acid equals hydrogen ions, or acid equals H plus, right? H plus is how you write hydrogen ions. You should associate H plus with acid. Now, if you want, for an independent work topic, this is also pretty boring, but if you want to, you can look it up. This is just how we're defining acid. There's other types of acids, and there's different ways of defining it. So as I'm teaching you this, keep that in mind. This is just how you're learning what an acid is. So don't go arguing with a chemist and they tell you, no, an acid is actually this. Remember, this is a 100 level class for non-biology majors, so don't correct them. But yeah, you can look that up if you want for independent work. So that's an acid. So then what's a base? Does anybody have an idea of what base may be? And I can give you a hint. Let's just think of acid or bases as something that started as water. So we had water, we broke it. It's not exactly correct, but it's good enough for this discussion. So imagine you have water, you break it, and you get acids and you get bases. So knowing that it comes from water, and knowing that an acid is an H plus, any guesses what water might be? Excuse me, what a base may be. Of course, that's a good hint. They keep saying water. What might a base be? Yeah, sort of. Think about what you're starting off with. What are you starting off with? What's water? H2O. Good. And we're saying an acid is an H plus, and I'm saying we got it from water. Not necessarily true, but for the sake of this conversation, that'll work. So what might a base be? Good. That's part of it. A base, you could just associate, again, if you're shorthanding, you could write base equals hydroxide ions, or more importantly, because you're probably going to see it like this more than the actual word, OH minus. And look, those things come together, right? H plus, OH minus, right? We know positive and negative things are attracted to each other. And look, when you put them together, what do you get? Two H's and an O, right? Water. So again, the way I described it happening is not 100% accurate, but for the sake of memorizing which is which, it works for that conversation. So yeah, an acid is an H plus, a base is an OH minus. You need to have that memorized. There will be questions, and I'm going to talk more about it when I show you the pH scale, where I say, all right, we went from a pH of this to a pH of this. What happened? And you need to be able to describe it in a few different ways. So if it's saying, let's say we got more basic, you would say there's fewer H plus ions, or there's more OH minus ions. I'll give a better example when the time comes. But for now, just associate H plus with acid and OH minus as a base. All right, so any questions so far? Again, it's going to get a little bit more complicated, but that's where we are so far. And I guess that could be the next word for attendance is acid. I wish that thing did proper circles. But yeah, acid is the next word for attendance. Let's move forward. So that brings us to the pH scale, like I just talked about earlier. I'm sure you've heard that word before, pH balance, or what is the pH? The pH scale describes the acidity, which is the measure of the concentration of H plus ions in a solution. So if there's a lot of H plus, it's acidic. That makes sense, right? Because I just told you should associate H pluses with acid. If there's not much of it, it's more basic. It's all relative. And another thing you definitely need to know is 0 is the most acidic, and 14 is the most basic. So if I had to give you something and say, all right, this liquid has a pH of 2, liquid A has a pH of 2, liquid B has a pH of 7, which one's more basic? You should say, oh, liquid B, because it's 7 is higher than 2. So you might get a simple question like that. More than likely, it'll be a little bit more complicated, and if you do the study guide, you'll see them. But another thing you need to know, as you're going up from 0 to 14 or down from 14 to 0, whichever, every time you make a step, it's a 10 times change in the concentration of H plus ions, which makes it a little bit more complicated. So if you go from a pH of 6 to a pH of 7, you could say that you are going, let's see, well, let's do it the other way. If you're going to a pH of 7 to a pH of 6, you could say, all right, there's 10 times more H plus ions when you go from 7 to 6. Here's where it gets more complicated because each step is a multiple of 10. So if you go from 7 to 6 and then down to 5, then that's a 100 times change in concentration, right? Because 10 times 10 is 100. And then if you go 3 times, then it's 1,000. Every time you're just adding a 0. That's a logarithmic scale, basically. So when they say you're going from a pH of 8 to 4 or whatever, right? That's 4 steps. So 10, 100, 1,000, 10,000. 10,000 times more H plus ions. Basically, it's a lot. And again, that's going to be tricky because there's going to be at least one question on the exam when I do say that. I say, all right, we're going from a pH of this to a pH of that. So what happened? So when you're studying that question on the study guide, remember that I'm going to change the numbers. I might change the way you describe it. And again, I'll give you another example once I show you a pH scale. But are there any questions so far? All right, I know it's a lot. Also know, again, I know this is probably boring. Most people find this boring. I do too. But sometimes you got to learn the boring stuff to learn the other stuff. So here we go. This is a good visual representation. Here's some pure water. Yes, there are some hydrogen ions and some hydroxide ions, but it's about equal amounts. So that's what makes it neutral. Here we have a basic solution that has more of the OH, right? More of the base. Here we have an acidic solution that has more of the H plus. Pretty simple. I guess I could give you a test question like that. I probably won't, but that would be good if you were in like 12th grade or something, or maybe 8th grade, right? Where I show you this picture and don't have the words at the bottom and say, which one's basic? Which one's acidic, right? Which one's neutral? But I probably won't do that. I don't like to make the exams too hard, but I also don't like to make them that easy. There we go. Here's a pH scale. You definitely do not need to memorize this. So when you're studying this, please don't feel like, I better memorize the grapefruit juice is a pH of 3. Black coffee is somewhere right under 5, right? You don't need to memorize that. But again, you will get something like that on the exam. And I'll say, how much, I might say something like, how much more acidic is grapefruit juice than urine, right? And again, you don't have to memorize that because I would give you this picture and you can just look and say, all right, so urine is a 6, so 5, 4, 3, so 10, 100, 1,000, right? So you would say 1,000 times, right? Because each step is a times 10. So you get that. And again, there's so many ways to describe it. We could say grapefruit juice is 1,000 times more acidic than urine. Or we could say urine is 1,000 times more basic than grapefruit juice. Or we could say grapefruit juice has 1,000 times more H plus ions than urine. Or finally, we could say urine has 10 times fewer H plus ions, right? See, I'm just describing the same thing in all those different ways. So just focus on that when you do study that portion of the study guide. Just think about all the different ways we can describe the same thing. More acidic, less acidic. More basic, less basic. More H plus ions, fewer H plus ions. More OH minus ions, fewer OH minus ions. And that's it. So anyway, any questions about this? I will point this out too while we're talking about it. So actually, I won't point it out. Let's see if anybody can see it. Anybody tell me what the pH of human blood is? Or about what it is? Yeah, it's actually, 7.4. Of course, you can't tell that with the picture. You can just tell it's something around 7, right? So it's about neutral. And I bring this up because a lot of people like to try to trick you into buying crap. And alkalized water is pretty much crap. Alkalized water is water that's a little bit basic. And some people are going to lie to you and tell you it's good for your health. I mean, water is good for your health, so it's not bad for you. But it's not going to do all these miracle cures that they tell you about. All right, how many of you have ever had lemon juice in a drink, right? He has, I have too. How many of you ever had grapefruit juice or a soft drink or tomato juice or black coffee? Hopefully you've never had battery acid. But all this stuff, right? This is really, really acidic. And guess what happens when your pH changes a little bit? That's another independent work topic too. If you want to look up exactly how much, you die. You can die. It needs to stay pretty much right there at 7.4. So if it gets too basic or too acidic, you die. Yet, here I am. I've survived a lot of margaritas, which is a lot of lime juice. I'll get with you in a second. I do a lot of black coffee, yet I haven't died yet because your body can regulate this crap. So alkalized water isn't going to do anything for you, just like drinking black coffee is not going to kill you, right? Anyway, yes, sir.
Is this number scale the same for, like, sound weird, but like pH scale for pH stuff?
Yep.
Like that same number.
Yep, any liquid, yeah.
So what is the average?
Well, it depends on the liquid you're talking about. Like, so water, pure water is a 7, for example. And that's also a good independent work topic. If you're curious, you might look up the pH of different stuff.
I had you talking about what is the average pH?
Oh, I guess 6, if this is correct. Yeah.
And that's crazy.
Right? It's a little bit acidic. Yeah. But yeah, that, again, that is a good independent work topic, I think, if you're interested in it. And you might not find the answer for everything. Like, I wonder what the pH is of my the protein drinks I drink. They probably don't have that information. But yeah. Anyway, any other questions? Okay. Oh, I like this one too. This is a good example. I'm sure no one actually did this trying to scare anybody, but they're kind of making a joke because, again, people will try to scare you using pseudoscience. And a lot of times when they use pseudoscience, they like to use big words. So especially when it comes to chemistry, because they're trying to scare you. Does anybody know what dihydrogen monoxide is? I don't expect you to, and I'm not teaching this, so you don't need to memorize it. But dihydrogen monoxide means 2 hydrogens, 1 oxygen. So it's water. Dihydrogen monoxide is water, right? So it sounds scarier, right? So I could say that, like, you could really flip people out if you want. You're talking about your kids, like, I give my kids dihydrogen monoxide when they're bad. And it sounds like I'm doing something bad. Like, you doing what? And then it says it's an acid with a pH level of 7. And if you don't know anything about acids or pH levels or what dihydrogen monoxide is, that can sound scary, right? But really what you're just saying is water is neutral, right? I mean, yeah, technically it's acidic if you're comparing it to the basic things, right? So yeah, dihydrogen monoxide is an acid with a pH level of 7. That's the highest pH level of any other acid, which is true, right? Because once you get just a little bit above 7, technically you're basic. But again, it's water. It's good for you. This is how people will try to scare you. And again, that one's just a joke. I don't think anyone's actually trying to do that. But the point here is there's a lot of chemophobia out there. A lot of times people it will list an ingredient and it sounds scary, but it's because you just don't know chemistry. Anyway, any questions about that? All right. You know what a buffer is? Basically, it's just something that resists changes in pH, right? That's how I wrote down what the book says. That's what the book says up there on the slide. But you could just think of something that resists changes in pH. How does it do it? Well, it just does the opposite of whatever you're doing to it. So if you're putting a bunch of acid in there, which is a bunch of H pluses, it accepts them. It gets them out of the solution. So you don't have a bunch of floating, a bunch of free H pluses around, right? Because that's what makes things acidic. Or the opposite. When things are getting a little bit too basic, the buffer's like, all right, here's some H pluses. Let's neutralize this. And your book pretty much just leaves it at that. Needless to say, kind of going back to what I was saying earlier, I've had black coffee, I've had soda, I've had lemon juice, I've had lime juice, all that really acidic stuff, yet I'm not dead. Reason is because we have buffers, right? We have buffers in our body. Without them, we would be dead. And because of them, you're not going to get any health benefits from drinking alkalized water. Well, the water is good for you, but the fact that it's alkalized, again, just a bunch of crap. I remember I'll never forget this, Gwyneth Paltrow has talked about something about she starts her day with her alkalized water and a squirt of lemon juice. I'm like, well, that kind of neutralizes itself, right? Because you have something basic and something acidic. But anyway, know this bullet point right here. Know what a buffer is. What I'm not going to do is ask you about this. Your book's just pointing this out. But buffers aren't foolproof. And your book points out that when carbon dioxide dissolves in water, it actually forms an acid. which lowers the pH in the ocean, which, as you might imagine, is not good for things, especially things in like corals, because their skeletons, their exoskeletons are made of something that's kind of dissolves easy in acids. So anyway, any questions about that, what a buffer is? All right, the next picture, I think, if I remember this slide correctly, should be, yeah, there's a picture of what we're talking about, right? So the carbon dioxide mixes with water. So we're having increased carbon dioxide levels in the earth because we're burning fossil fuels and things like that. That mixes with the water. This leaves you with carbonic acid, not that you need to know that. But yeah, and then that bleaches the coral. One of the things that bleaches the coral. So any questions about that? Okay. That's another picture of it. Looks pretty horrible. But that's sort of like that first picture I showed you at the beginning of the chapter. I said, what is this a picture of? And someone said correctly, that's a coral reef. And it is. And even though you can barely see it because it's really blurry, there's a bleached, dead piece of coral. All right. As always, every chapter ends with this, the evolution connection. So just like every chapter has a process of science section that we skip, it also has an evolutionary section that we skip. So you should read it, understand it, ask me questions if you have any questions about it. There probably will be questions on the study guide about it, but there'll never be questions on the exam about it, unless I say otherwise, but it's almost never. So anyway, yeah, you can read that, read about it if you want. That's all about radiocarbon dating, right? So I'm sure you guys have heard of carbon dating. You can learn about what it is from that. And that's it. So are there any questions? But I guess, hold on, the last word for, no, I won't even do the last word for attendance. Just like last time. If you're live, send me those words before 9 a.m. If you're watching a video that I posted to Google Classroom via YouTube, then like the video and take a screenshot that proves that you did that. And that's your last part of the attendance. So any questions? All right, we got out of here early today, sort of. Wow, yeah, 12 minutes. So if you're new, please stick around. And if you're not, I will see you in lab either Monday or today, or I'll see you back here on Wednesday.